We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
All right. So guys, today we have another lab on our Precision Agriculture 412 course on remote sensing. It's a very special day. We learn a lot about things that goes way above my head, and I'm sure that you guys will be having a good time today. Before I get into that point, we do have a quick outline here. So I'll be doing the speaker introduction. Then Karin will be unfolding her presentation. After that, I understand Karin will have a couple of minutes for question and answers from you guys and from myself. And then we say goodbye to Karin, and then we can talk a little more about what she present to us, and if there's still some burning issues or some need for recall, we can just I can just bring to her attention and get some clarifications to you. And then we'll have a quick intermission, 5 to 10 minutes. And then we talk about what will be our next lab and some other business related to our class before you guys go for your winter break. So it is my great pleasure to introduce to you guys Dr. Karin Langona. She has the title of a North America Product Group Manager for the Pro Commercial Vehicles. So that's a lot under her belt in terms of responsibilities and engagement with the automobile industry. So I had some people these days ask me, like, Yuri, how could you manage such a great speaker, high caliber speaker to your class? Well, I tell you what was the connection there, guys. So this is Karin and I on a few springs ago. There's one there is about 4 years ago, and I was the kind of the strange kid like that in the middle. And then Karin was holding my sister. And then the other picture is us here in Canada about 15 springs ago when she came to visit us in Guelph. So that's where comes the connection. Karin's my cousin. And yes, I think that we have a great time today with her talk. Okay. With that, Karin, please.
Okay. So thank you for having me this afternoon. It was my pleasure. Although Yuri and I are cousins, I'll be talking about a topic that is very close to my heart. And I do hope I'll give you inspiration so you can apply connectivity on the field, I would say. I'll be focusing today mainly on what we call connected and autonomous vehicles, but I will spend some timing on the various sensors that we use, not only at Ford, but industry level, correct? I do need to go through this, a disclaimer that everything is stated in this presentation is to be considered my own opinion, not an official representation of Ford Motor Company or any of the Ford employees. And all the content that I'm presenting today, you will be able to find on Google. It's public information, so no private information here. And I started my career in academia, and I was born and raised in Brazil, but Michigan has been home for about 14 years. And I decided to move to private sector and work with technology applied to what I call real problems. So I have been in the cloud, vehicle, and telecom industry intersection for 10 years. So vehicle platforms is something very interesting to me. So let's start talking about cars. I know apparently you already had some talks this morning, but I would like to show you that there is centuries of evolution to get where we are today. And I decided to base my evolution timeline here on the engine or on the motor of the car, because it's easy for everybody to understand, not very specific. So as you can see, in the 1770, they thought that having a steam-powered vehicle would be a great thing, and it was by them, of course. And then in 1903, and I decided to portray the Model T from Ford. Of course, I work for Ford, but Model T was not the first gasoline-powered engine. We had others before. The innovation of Model T was to bring vehicles to the hands of everybody, and also to start the production line, the concept for automation in the manufacturing domain. Then the first diesel engine started in 1936. So the first vehicle with a diesel engine based in Europe, the Mercedes-Benz, the 260D. And in the 80s, it was very popular, I don't know in Canada, but in Brazil and here in the US, what they call the flex fuel engines, where the same engine can work with gasoline or ethanol. And the ethanol can be made by corn, the raw material, or sugar cane. So different ways to get the ethanol that will become the combustion for the engine. In 1999, early 200s, and by the way, the picture there is the really first hybrid vehicle, which is a Honda Insight. People think it's a Honda Prius, but the Insight was the first one. It was, in fact, displayed in the auto show here in Detroit. And then today, every time you open the news or a website, or if you watch games and you see commercials, we are going into the electrification era, moving the vehicles to zero emissions and increasing the utilization of electric vehicles. So this is where we are today. Okay, so to show how the evolution, and we are here today to talk about vehicles that are connected. What does that mean? It means we manufacture vehicles today, and by the way, all the vehicles from Ford, they come out of the factory with a physical part that is called telematics control unit, or we call them modem. So the modem is very similar to your phone, because at the end of the line, we call provisioning. Someone or a robot goes there and put a SIM card in the modem, which it is the same card that you have on your cell phone today. So a car is provisioned by a SIM card, and that SIM card has to operate with a particular carrier. Here in the US, the Ford vehicles are served by AT&T, but it could be any other carrier, as we have many carriers. So the TCU is the physical part of the vehicle architecture. Of course, it has the in-vehicle software as well. Then you do need the wireless carrier that will make the connection for us. It has the infrastructure similar to what we do for our phones. And it is where the word connectivity comes into play, because you have a connection vehicle cloud. So the conduit to this connection, it is the wireless communication based on cellular connectivity. And then from there, you can make the either vehicle talk to vehicle, or vehicle talk to an intelligence infrastructure if you have an intelligent traffic light that can warn you that is about to turn red when you are several miles away, so you can reduce your speed, for example. You can have conversations or exchange signals between the vehicle and the pedestrians. And so the pedestrians that are not paying attention when they are about to cross the road, it could be warned on their phone that a vehicle is approaching. So this is other ways of connectivity. It's very common in the industry to see people saying V2V, V2I, V2P. It's exactly what I just explained on other ways of communication. And the software portion comes because it resides on the cloud. So once you get connectivity, you can talk to the cloud from anywhere if you have the connectivity. And from the cloud, you can have a multitude of applications, not only to work with the vehicle, but also content. For example, you could download a new version of the map. You could download advertisements if it is not a car that has a driver, if it is an autonomous car, for example. So, and you have other concepts that we talk about today that because the vehicles are distributed, we talk about edge computing. So you bring pieces of the information closer to where the vehicles are, correct? So that's the whole explanation of what a connected vehicle is. You can also make a vehicle that is not connected from factory to become connected. And my next slide is showing this to us. So you could, for example, Ford sells a little device called OBD2 connector. So OBD is a port that almost all the vehicles manufactured since 1996, I believe, they do have that port somewhere in the vehicle. And you can, this little device that you see on the screen on the left has a SIM card as well, sometimes has multiple SIM cards, and it does the same function as I was explaining as the TCU that you also see on my picture. So I'm trying to show you can either make a vehicle to become connected by adding a connector to it, and it will have less data that you are able to read, or it comes from the factory as a connected, native, as we call, natively connected, and it has a modem. And the modem is provisioned to the vehicle based on the network. So nowadays in the US, our network here is 4G, 5G, because the 2G already died, and the 3G is on the last couple of months. In fact, some of the carriers are ending their 3G operation this month in the US. This picture is also showing that you can have a mobile app running on your iPhone or your Android phone. And from the mobile app, you can take actions towards your vehicle. For example, you can check the oil level from the app. You don't need to go into the front part of your car, look where the oil container is and check the level, or check on inside of the vehicle. You can also issue a command to maybe start your car, remotely start your car. In the morning is very cold. I'm sure for you it's colder than for me here in Michigan. So before you leave home, you go to your app, you press the button to start your vehicle, and your vehicle will start. In the case of Ford, they usually stay on for 15 minutes and then they turn off if you don't go there and start driving. So Ford Pass is our mobile app where you can do several things from distance because you do have the connectivity. And inside of the car, we have the integrated experience. So if you have an Android phone or an iOS phone, you can mirror your phone into the screen of the HMI, and you will be able to use not all your apps. So you won't be able to have your Instagram running there, but you will be able, for example, to use Waze, one of the applications from Google, to help you drive around town. So it's really an ecosystem, and although I'm using Ford as an example, most of the the OEMs or auto manufacturers, they have similar solutions. So when Ford started this concept of connected cars, we started back in 2014, relying on a 2G network. As I said, that is no longer existent. And today on the roads around the globe, Ford has about 6 million of vehicles that are connected. So we are able to see all their signals from the cloud, where they are, where they have been. And we expect to increase this number to 33 million by the end of 2028. Okay. So Yuri, is it planned to ask questions at the end, correct?
Yes.
Okay, good. So here I'm trying just to illustrate, I already touched on this, but it's just to complement that connect vehicles, as you can see, connectivity and cloud are a perfect combination for you to tackle. Again, you can download new software to your vehicle, which we called over-the-air updates, so OTA. So you can bring something new to your vehicle if it runs on that same hardware. And you probably see this a lot of times on the news. If you're familiar with the Tesla brand, they are constantly doing OTAs. We do as well. Ford does as well. So a vehicle that is connected, you are able to update, you are able to send new features, you are able to fix a glitch because you trigger the download from the cloud. You can improve the map definition if you collect data where the vehicles are driving, and if you feed your maps and then you download better version. You can also apply artificial intelligence to help make decisions, provide systems more intelligent in the vehicle. And I'm going to talk about it. There is a couple of examples already on the road here. All of this doesn't come for free. It's wonderful. I love my connected vehicle. I love planning new features for it, but there is an increased complexity in the system. So the vehicles are no longer just mechanical. When you say, I'm taking this vehicle to the mechanic, it's really much more complex than before. And I have chosen just a couple of numbers to show you why is that more complex? How can you tell us that is more complex? So in 2010, if you would look at the cost of a vehicle, the electronic components, it was really about 27% of the total cost of producing that car. Last year, it reached about on industry level 40%. So almost half of the cost of the vehicle is really because we have electronic components. And when I say electronic components, which in my industry, we just say ECUs, and people understand what we're talking about, it's every single embedded system, embedded sensors, a little CPU that you add, a little chipset that you add to the vehicle for a particular reason. This explains to you why the chip shortage that we're facing is really impacting production. We can't sell vehicles, like deliver vehicles enough because we don't have the electronic parts. And as you can see, I also post here a forecast that by 2030, the cost of electronic components may reach 50% of the total cost of a vehicle. So it means more complexity in terms of components, many more millions of lines of codes, because each one of these components usually entail lines of codes, much more data that you are able to either download or upload from the vehicle. And I created this just for you to compare in terms of progression. It's just to show back in 1969, when the first man put the footprint on the moon, the core piece of the Apollo 11, which it's called AGC, the Apollo Guidance Computer, was the main piece of what you see the picture on the right, had about 145,000 lines of code. Okay, a lot of lines of codes, but this was 52 years ago. Then the Ford GT, the blue vehicle, it's a sports car. We have not too many units, but it's sold in the US. And it's a nice sports car, but a small car. And the example I got here is model 2017, has 10 million lines of codes. And it can generate 100 gigabytes of data per hour. Of course, we don't collect all that data. You can imagine how costly it would be, but just to show you how the complexity has been increasing. And autonomous vehicles, which is a picture here in the middle at the bottom, will have billions of lines of codes. We already have that number today, and petabytes of data. So increase the complexity but also increase the business opportunities, I would say. All of this also has challenges because each manufacturer has its way of doing things, its architecture. So a lot of the solutions are proprietary solutions. They have different vehicle architectures. The modems that I'm talking about that we have in the vehicles, they are very manufacturer driven. So a modem from Ford does not work on a modem from BMW, for example. The vehicles are exposed to extreme temperatures, vibration, and humidity. So in order for us to have a SIM card always in place that resists to all of this, it requires a resilient hardware, much more resilient than your phone. If your phone overheats, it stops working in a couple of minutes, you are able to get it back. But the vehicle is different than the phone. And also the life cycle of these technologies, software, hardware, and telecom or infrastructure are very different. As I mentioned, in 2014, the vehicles got a modem 2G. But if you still drive a Ford 2014 today, it has zero connectivity. It lost that capability because the 2G network is no longer around. And as you can see, this is happening with the 3G network. One thing we are doing since last year is asking the people who are driving Fords with 3G network modems to come back to their dealers, and we are able to replace that physical part. But not always possible because it has a lot of implications with the architecture of the vehicle. The modem is just one piece of many parts that the vehicle has. Okay, what else can we add to a vehicle to make it more intelligent, more safe, more reliable? And this is what comes, I think, is the intersection of what you guys have been studying, the vehicle sensors, and what the vehicles have today. So I would say all the vehicles, doesn't matter how expensive, how cheap, what is the brand, what is the make, they all come with a variety of sensors. And my list here on the screen is just a few examples that I thought you guys will be able to recognize all of them just because you drive a car or you sit in a car, but the list could be several pages long. So we have few temperature, few pressure. I'm not going to read all of them, but it gives you an idea. It's very easy to embed a sensor in the vehicle for inside experience, what we call in-cabin experience, or for outside of the vehicle to be able to recognize the surroundings, to guarantee some safety to the occupants of the vehicle, to make decisions. Lane departure warning is one of them, very used today. Like either the car tells you, warns you on the panel, or make any sound, or vibrate the steering wheel, or simply moves the steering wheel so it guarantees that you don't depart from your lane to cause an accident. So there are many ways to tackle a problem based on a similar sensor. The self-parking sensors, we have lots of sensors supporting the parking functions. It can be because I am parking and I need warnings, how far or how close I am from the cars, from the objects, from the curbside. But it can also be a car that self-parks. So the car needs all the inputs to be able to self-park itself. So in that case, it needs much more sensors because humans can also use our sensors, correct? So I decided to talk a little bit about the most popular ones, not only for connected, but also for autonomous. One of them is the radar. So radar sensor is a wide spectrum of sensors. It's based on their frequency. So you are going to see, and if you Google, several types of radar sensors, but the core for them is to detect texture, or detect objects. And in this case, it's to really warn or sometimes to avoid a collision. It really depends what you do with the information. Once you detect an object or a vehicle, you can warn the drivers or you can make the car stop. It depends how the manufacturer of the vehicle decided to use that information. Radar sensors are used for parking aids because they are the ones that detect objects. Lane change assist, so before you change lane, you need to recognize that there is a space there and there is safe for you to move lanes. So that radar is used in that regard. And you're going to see in one of my slides when I talk about driver assist, an intelligent cruise control, then relies a lot on radar. So it relies on the radar sensor to calculate how far I am from the vehicle in front of me. Do I need to reduce my speed? Do I need to quickly reduce my speed? So the radar is the sensor that we use, usually around the bumper. And another reason why it's a great sensor where you're going to see in a lot of the vehicles is because it's not affected by the weather. The waves that it sends, it's not based on light, so it is not affected by fog, by ice, by snow, by light. So it's really not affected by weather, so makes them very reliable. Radar sensors are also used to detect the surface. So you're able to distinguish, is this an asphalt or is this a dirt gravel road? Or do we have a layer of ice? So there are, depending on the precision of the sensor, you are able to go to that level of understanding. And for autonomous vehicle, that is really important. For example, you and I, we can drive a vehicle that does not recognize the surface of the road because we know the surface. We adapt our driving style based on the road. But an autonomous vehicle, if you need to provide that information so it can decide what is the speed, what is the torque, what is the tension that it applies to make that machine to move. The next one is the LiDAR. So LiDAR is a kind of debatable because there are people who believe you can create a completely automated vehicle and don't use LiDAR, which is what Tesla does. So Tesla has no LiDAR in their solutioning. You're going to see I put a summary of their solution. But most of the larger manufacturers, if you look at Waymo from Google, if you look from Aurora, if you look Cruise from GM and Ford, all their prototype vehicles, they do rely on LiDAR. LiDAR is no more than a rotating bin of laser light. So that's the reason you see LiDARs very on top of the vehicle, or sometimes on the sides, but on the highest points, because it emits the laser beams to scan the surroundings. And as the laser beams reflect or detect objects when they're reflected back to the sensor, the vehicle is able to create an image what is around. I'm overly simplifying here, but this is the main principle of LiDAR. It is really detect surroundings. And if you say, okay, why do we still need radar? Radar really detects based on the distance. Is there an object there? Is that an object that is a plastic bag with air versus a piece of concrete? So the radar is able to distinguish those. LiDAR is to recognize surroundings. It's based on light, so it is affected by the weather. And there are two types of LiDAR today. One is the electrical mechanicals. Really, you can see it turning. It has mechanical parts. And the solid state. a more modern approach of building LiDARs. The other one is the ultrasonic sensor, also used in parking assists. A lot of the ultrasonic is regarding curbside, pedestrian detection. A lot of the self-parking systems rely on multiple ultrasonic sensors. They work on high frequency sound pulses. They also are reflected by the objects near the vehicle. This is the reason they are used when in parking situations, because easy to detect the curbside, any other object that you have there. The way they calculate is really based on they emit the pulse and calculate the time it takes to come back. So they're able to estimate the distance from where the vehicle is to the object. And then they use that distance to move the vehicle. So if it is in a parking situation, that what I just described is going to happen multiple times until you finalize the parking process of the vehicle. And the last one that, although we call a sensor, is really a camera, but we do call camera sensors. It can be a very, very tiny one, but it is a camera, no different in principle from your phone camera, from your regular photo camera, where you're able to, from the picture, draw conclusions. You can be a camera that shows the rear of the vehicle, the front of the vehicle. We do have systems, Ford does have one that is called 360. So you have a view of the entire surroundings of the vehicle. And I do know, like based on a couple of messages I exchanged with your professor here, you can use image also to track the animals on the field. On the bottom part of the slide is really showing what the manufacturers are doing today. So Ford has a hands-free mode available on a particular vehicle. So the Mustang has a version that is called Mach-E. It's a fully electric vehicle on the market for 2 years, very good ratings. It does have a driver-facing camera because it wants to make sure your eyes are on the road when you activate the hands-free. So that camera is really dedicated to make sure you are still paying attention on the road, although you need some brake and you has activated the hands-free, because it's a hands-free mode, not a fully autonomous vehicle. The Tesla, if you're talking about the autopilot for Tesla, it is a 360 view because the car make decisions fully by itself. It relies on 12 ultrasonic sensors, as you can see in the text there, 8 surrounded cameras, in order, and you see that how far the car can see, up to 250 meters in range. And it's able to make detection, as I mentioned, what is hard objects versus soft objects. And it is an improvement, as they are saying here. They can see twice as much the distance from the previous version of the Tesla Autopilot. And this comes directly from their advertising material, by the way. And Cadillac is another one that has surrounding vision. They rely on 4 exterior cameras. And I wanted to show that each one of them is capable of a 2 megapixel, what they call bird's eye view. Again, for all the surrounding, everything around the vehicle. And as you can see, if you drive a vehicle that has a trailering integration package, you will have up to 9 cameras to be able to see your trailer, park your trailer, have a safe experience with the trailer. So this shows how this is already part of what we see on the road. It really depends on the model that you are looking at. I selected a couple pictures a little older to show you, for example, since 2013, which we no longer manufacture Fusions, but I wanted to show you, already had these sensors that I mentioned, radar, ultrasonic, and the camera-based ones and their locations. So the picture is trying to show you that you do have like front and side radar, you have a front or rear view camera. This is the idea of the picture, and it is from 2013. This other example, more scientific, is showing you what we call basically sensor fusion, because you have all the sensors in the vehicle. I like this because it's showing you the different frequencies. It's also showing you what are they used for. Blind spot detection, pre-crashing sensing, lane change assist, parking aid. So it's really showing you each one of them has its function. There is a reason why some are radar, why some are ultrasonic, why some are cameras, and it has to do with what are they able to provide, the cost, how they operate depending on the weather. So that makes, when the engineers are creating the sensor package, they take all of this into consideration. And as I was talking about the ultrasonics, I wanted to show in the F-150, which is, I don't know in Canada, but in US, it is the most sold truck in the US, good for Ford. And I want to show, so the full vehicle on the left, but the arrow is showing you one of the ultrasonic, the parking sensors that I was talking about, usually very close to the curbside, so you're able to get the data, calculate the distance more precisely. And this is a picture showing that all of this for a fully autonomous vehicle is even more important because there is no driver. So it's no warning system, it's really an operating system. As you can see the LiDAR on the top, the green part that you see on the car, we tend to call it a tiara. So the vehicle has a tiara with the LiDAR on top, very common for the autonomous. And besides of all the sensors, of course, we have to process all this information. So there is a central computing unit. And for your comparison, one of the industry standards, like if you're to decide to manufacture your own car today in your garage, and you say, Karen, I do need a central computing unit. Which one should I buy? And I would say, okay, if you really need a powerful one, NVIDIA, the company that makes the gaming processing, also has a nice computing platform. And that computing platform, just for you to compare processing power, is equivalent to 140 MacBooks in computing power. So you can have in a vehicle just one computing unit that is equivalent to more than 140 MacBooks. Okay, and the last part of my talk today is, okay, we went from connected to take a little bit of a look on the complexity, sensors, and let's look at the future. So the future is really about automation. You want to take your vehicle from where we are today, which is level 2. So in the US, it's very common for us to talk about vehicle automation based on levels. And this is a full explanation of what levels are. So a level 2 is the vehicle has a lot of functions that can be automated, but it still requires a driving all the time there responsible for the task. So a Tesla autopilot, it is a 2.8, 2.9. It's really a partial automation because when the autopilot doesn't know what to do, you have to be there and take over. When we talk about an autonomous car, we are really talking about level 4, level 5. As you can see, the driver is erased from the picture basically to say, in a level 4, you can define a geographical area and you can define weather constraint, and the vehicle will operate autonomously. So you can say within a certain area in Toronto, considering that there is no snow, no ice, no heavy rain, the vehicle can operate autonomously. So that's a level 4. But if you say the vehicle can drive from West Coast to West Coast, regardless of the weather, then we are talking about a level 5 automation, which I think we are many years away from that one. The autonomous vehicle ecosystem, we tend to look at the vehicle and think about is all autonomous vehicle, but it's not only the vehicle. The vehicle, yes, for sure, but you need the intelligent part that makes the vehicle to behave as a robot. So this is what we call in industry terms, automated driving system. You have a set of software, resides in the vehicle, makes the decision, receives the inputs from the sensors, decides where to go, what is the speed, when to turn. So that is the ADS. And we have a lot of services on the cloud. For example, you can keep your mapping on the cloud. You only download what the vehicle needs. Or you can have commands that you can issue from the cloud. So you have a digital platform, or as I said, you can have interior screens because there is no reason to have a driver. So you can have nice screens and download a video, download a game, download advertisement. So that is the role of a digital platform in the EV ecosystem. So the vehicle relies heavily on what we call sensing, which we covered before. So radar, cameras, LiDAR, ultrasonic are the vehicle's eyes, basically. And then the vehicle takes all this sensing, process that sensing to create what we call perception. How do I perceive, or how the vehicle perceives the surroundings? And then makes the decision based on the perception, and the decision causes the motion. It is really what happens in every movement. So every time you're watching a video, if you see a cruise vehicle autonomous in San Francisco, all these 4 steps are happening all the time. Sensing, perception, decision-making, and motion. And motion is really finding the correct actions. Do I turn? Do I increase the speed? Do I reduce the speed? So it's really how the automated driving happens, right? So heavily relying on sensing. The better sensing, better perception. And between perception and decision making, there is a lot of artificial intelligence, machine learning involved. So if those are areas that you have interest, a big demand there. And just to end here, a couple of players in the US. We have Cruise, as I said, from GM. Waymo is a subsidiary of Google. Ford, of course, working with Argo AI, our partner on the SDS. The blue one at the bottom is Aurora, a company that started as a startup, but they acquired the Uber branch of AV. And another segment that we're seeing more and more autonomous is trucks, long-haul trucks, large freights. And TU Simple also started as a startup, but is already a public company. Aurora in the middle, and Waymo also from Google. So the two they operate vehicles and large trucks. And by the way, if you look at the pictures, you see LiDAR on top of the vehicle. You see LiDAR, as I was saying, they all rely on LiDAR cameras. And for trucks, they have many more sensors. Same type of sensors, but many more because of how tall they are, the size of the trucks. I want to talk a little bit more about the level 2 automation because we do have this available on the market today. So if you drive a Tesla or if you rent a Tesla today, you will be able to experience the Tesla autopilot, where your hands, the system does check to make sure your hands are there. So the time in time, you have to press the steering wheels to make sure, yes, I'm here, but the car is able to accelerate, steer, brake, and the picture on the right, on the middle, it's exactly from a Tesla view when you are on a Tesla Pilot activated. So you are seeing where the car is going, the speed there, 24 miles. Ford Blue Cruise is a very similar version of autopilot, not fully autonomous, but a much more intelligent cruise control. And also GM Super Cruise. So at the bottom, you see a Ford Mustang, and the top is the Cruise. And you can see, if you on the picture, I hope you can, it's showing changing lanes. So the car is able to rely on the sensor, as I told you, change lane, detect that is safe. The car can maneuver itself without the driver touching the steering wheel. And each one of them does differently. As I said, in the Ford vehicle, there is a driver-facing camera to make sure the eyes are on the road, and the head is really positioned looking up front. In the Tesla one, there is a steering wheel sensing, and in the Cruise, they rely on visual prompts to make sure that you're paying attention, because they automate your experience, but when they don't know what to do, you are supposed to pick up the job and continue driving. So it's a level 2 partial automation. Okay, so I think we cover a lot today. Started with connected, cover complexity, cover the main types of sensors that we see in connected and autonomous, and ended with just a quick snapshot on autonomous vehicles.
All right, thanks so much, Karen. It's a lot of information for us here. I think it's quite inspiring. So I think that we probably have a couple of minutes to answer some questions for us. Yeah. Just had something, that's all good, right, guys? Yeah, not a problem. Okay, guys, how you are for questions? I do have, as always, a list in my mind here, but I'm open to you guys. Who would have the first one? Walker, man.
What's the coolest part about your job?
I think the coolest part of my job is to really see the progress, because we test in Miami. It's our main city. We do test in Detroit, Palo Alto, Austin, but our main city is Miami, and you can understand because the weather there is quite nice all the time. It is really nice to be able to be in Detroit with a phone app and request a ride, similar to what you do for Uber, but I am interacting with the fully autonomous car. We do have safety operators to make everything very safe, but I know that is a car that is receiving my command from here, is taking action in a completely different city where I am. So I think it's very cool to see how far technology has gone to allow that type of thing to happen. But also I do expect to see that as part of our everyday life, correct? So if you're too tired, you don't want to drive, or you are unable to drive, you would have the safe vehicles and a great experience to take you from A to B. So I think it's the coolest part is to really see the advanced technology really on the road. Great question. Thank you.
Okay, Karen, from my end here, how works the R&D process for you? Like where the inspirations come from, and then you always have the moment of sandbox when you you see if it's feasible or not, and then sometimes things that a plan maybe just doesn't work. But how would it be in general terms the R&D process for developing all these technologies?
So we do have it's called Future Tech team, who keeps exploring what is possible, what is not possible, correct? We use a lot of Raspberry Pis sometimes to test our ideas. We use very small vehicles, I say, to see if the idea is feasible. Lots of labs. partnerships with universities in terms of research that Ford funds. We have large grants per year. And once we notice that the trends on the market, once we notice that the technology is more mature, it can be applied to more than one vehicle program, then you will start thinking, okay, from an R&D perspective, it goes into prototyping. It doesn't mean it's going into a vehicle, because to go be part of a vehicle that will be sold, it has to be a technology that is already commercial for safety reasons, regulatory reasons. Like, I do have prototypes today that we test. For example, we're trying to test unlocking the door with a keypad, and we're using Raspberry Pis. No problem at all. But Ford is not going to sell a car that has a Raspberry Pi for you because it's not reliable, not safe for the customer, not a good quality. So then in order to become part of a vehicle program, it has to be more at the commercial level, either because it is already commercial or Ford makes partnerships. For example, a couple of years ago, we invested in Velodyne, which is a LiDAR manufacturer, to help them advance the LiDARs, because we rely on the LiDAR to advance AVs. So it is a partnership still in the R&D space or phase that envisions the benefit in the future. But mostly what you see on the vehicles on the road, they are already passed from the R&D. And we do test things that are, I think you guys will like this example, still related to sensing. Ford has a couple of vehicles that has a feature called phone as a key. So the vehicle has about 11 Bluetooth low energy antennas around the vehicle. And if you say, what's the size of these antennas? They're very tiny. For example, you have them on the door handles. If you enable your phone to be the key for that car, so you go through enabling on the HMI, when I approach the vehicle with the phone in my pocket or the phone in my bag, the car unlocks automatically, and I can drive the car without having the key fob with me. So that is a connectivity at Bluetooth low energy, for example. And we tested many times, because you see the number of antennas that you have impacts the cost. Could you have less antennas? But then the system doesn't work super well. If your angle is slightly different, your phone is still in your pocket, but the car cannot sense the phone, doesn't lock the door. So there are a lot of these processes where the technology is on the road, is available, but you still feel that it's not 100% super reliable, in the sense that it works the same way, repeatable all the time.
Awesome.
Are you like working with and developing the Ford Blue Cruise? And then also, why can you only use it on certain roads in Canada and the US?
You are saying why are they only used on certain roads?
Yeah, like, is it because they're like, just what's the logic behind that?
The logic is probably because based on how much they can process, like the roads that are wider or have better signs provides better inputs to the vehicle. If they are too narrow, the lanes are not quite visible, too many turns, or no lanes at all, then the vehicles, the sensors are not capable to get good inputs. So the decisions would be very poor and not safe for you to drive, correct? Don't take my answer as completely, because I was not the one fully involved, but this is based on what I know would be how I answer your question.
Awesome. What else, guys? Please, Miranda.
What is a piece of technology that you're looking most forward to being completely developed?
I think there is not a single piece. I would say because we rely so much on wireless, it would be nice that wireless has a full coverage all the time. You know that's not true. I don't know your experience in Canada. Here in the US, in certain parts is great. You never have a shadow. You always have several bars of signal. But if you are sometimes under a bridge, there is no signal. So I would say because of the heavy reliance on connectivity, it would be nice to get in a stage where wireless works all the time, everywhere. But I'm not sure if we'll be able to get there because it requires a lot of more investment and technology changes. So currently we do have 5G here. 6G is target for 2030. So it's always changing, but that would be the piece of technology that would help everything I explained to you guys today, but also other industry, like the medical devices, that people can wear devices to help with their signals, correct? Your blood sugar, your pressure. So I think it would really helps because they also rely on connectivity. So you could make a much more connected world if the wireless would be more reliable. So that would be the one. If you ask me for a wish, that would be my wish.
Karen, how much inspiration the automobile industry gets from the aviation or other industries? Like how much you guys can learn from other uses of technology?
A lot, I would say. By the way, all these sensors that I talked about, the airplanes already have many of them for many years now. So they really some of them really trickle down from the air in this, because your question is more from the aerospace industry into the automotive industry. There is a lot of exchange, I think, from industry to industry, from automotive. You also see from agricultural equipment. So if you talk about them in terms of automation, they can be much simpler than vehicles, because the complexity for the vehicles is if you're driving in a busy city, you have other cars, you have buses, you have bicycles, motorcycles, people, dogs, boxes. So it's much more complex if you think if you have a machine on the field during harvest time. It would be less constrained, less inputs that they have to consider, correct? The other day I saw a solution where they use drones to collect, I think was apples, but it was a larger fruit. The drones would collect the apples and bring to this central vehicle. So the drones don't go too far. They are basically around this vehicle. And I thought, okay, much cheaper, less constrained than the automotive industry, because our top one concern is safety, reliability, because if anything goes wrong, we're talking about lives, not only the passengers, the occupants of the vehicle, but the pedestrians, correct, the other vehicles. And in other industries, you may be able to go faster or find other solutions because you have less constraints. But we certainly learn from the aerospace industry because they do have safety as well, much more than us. And we also pass downstream based on what we learn for other industries as well.
And Karen, that's one thing that I worked a lot in the past was thermal imaging. And is that thermal imaging a feature that would be important, like for automation of a vehicle, or not so, maybe secondary? Like how you see the thermal imaging use on that?
So in the autonomous vehicle space, thermal imaging is used. Not super advanced today, but yes, certainly a part of it. Because again, the car has really to know everything, sensing everything that is around it. But we'll rely on every single possible input to accurately recognize the surroundings. What we have today on the industry, like in regular cars, we don't. I can't think of a feature right now that I could say, oh, we do use that type of technology. But for future, yes.
Okay. And you answered to Miranda what we'd like to see going on, and you talk about connectivity. So that's one of the sides of it. But when it comes to sensors, do you see any bottleneck from just for the sensing side of things, not like the connection, but what you could be sensing better to make the technology more robust or more reliable?
So all the sensors still have a long ways to go, not only in reliability or how capable they are, but in terms of reliable robustness. Because as I said, attach a sensor to your watch, to your Apple Watch, it is much more delicate. But attach a sensor on the bumper of a truck, it has high temperature, vibration. It can get hit by a rock, and ideally it has to still to function in this very rough environment. So the sensor, all of them still have ways to go in terms of robustness, how small they are, because if they are too large, then not only the visual aspect of it, but also you need space in the vehicle. Another one is how much power they require, because power consumption in a vehicle also went up, because all these ECUs that I was talking about, all these sensors, they needed to be powered. So you need power for all of them. Another aspect that can be improved. In terms of cameras, the precision, or what can you derive from the pictures that they are collecting from the environment. So all of them have a lot ways to go. So a lot of opportunity to keep developing the sensors. The one that I talked about, where the vehicle recognizes the surface of the road. You don't have it today in vehicles. You have more in labs, still very expensive. There is no manufacturing, like high volume manufacturing process. And even for the LiDAR, this idea to move to solid state, because it's more reliable than mechanical parts, we don't have it's still a very manual process of manufacturing. So all of them have lots of opportunities to improve. I would say there is none that that I say, okay, it's so improved, so small, so cheap, blah, 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 that there is almost tiny bit to make it better. I think all of them is still possible to be better.
Other question, folks? Karen, for how long will you still be having cars drive on roads? Are you still, I'm asking that because this morning we had a conversation about tractors, and you're just going through like all the way when you use a horse to pull equipment, and then came the tractors, and now we no longer want a driver in the tractors, so then it'll be a driverless tractor. And then you're just in class like, okay, what would be the next? And some of us said, oh, maybe the tractor will no longer be touching the ground anymore, because if the tractor doesn't touch the ground, it's not compacting the soil. So for agricultural side of views, it's kind of nice, I think, because it's just doing the work without touching the ground, almost like a huge drone or something that would be not connected to the ground. So for your perspective, how you see those moving or changing, like from a car perspective?
It's a more personal opinion than a scientific answer here. I think humans still like to drive. Of course, the younger generation, we see less folks interested. They think it's maybe easier to take an Uber or a Lyft. So yes, we do have less people driving. but it's still a lot of people interested in driving. Considering the technology is not fully mature, so my personal opinion, it will take at least 10 more years for us to see fully autonomous vehicles on mainstream. I'm not talking about what we do in Miami today, is still prototyping. If you think, will cars disappear? Well, then a completely new way of transportation. If we're able to teletransport ourselves, then probably yes, nobody will be interested in sitting on a car if you have something simpler, faster, safer to do it, correct? But I don't see that technology around. So I would believe cars, we'll still see cars for several decades on the road, and a mixed fleet, automated and human-driven, is still on the road for quite some decades, is my personal opinion.
And one last question, Karin, just from more for historical perspective. When you look forward to other companies, you give us a timeline for some development in terms of the engine. Is there some on the granular level that you can walk us in some devices that how they change over time? What do you consider some other milestones that you see as important for the development of the cars besides the engine?
You could take several domains. I would say the braking system is one. If you're focusing on if you see how the braking system changed over time, you can do a timeline based on sensing. For example, the first sensors, I think, was 1950s. And it was just to warn you, like at a temperature. So the first sensors were related to engine temperature, and it would just show a light, which we do still have a lot of lights that pop up on the HMI or on the cluster, but not help you drive the car. So if you can do a timeline based on sensing. I think the engine covers a lot of where the future is. There is also the style. People say, for example, Ford no longer manufactures sedans today. If you would like to buy a car from Ford, the only car that we really sell is the Mustang, the sports car, and the GT that you saw, but no other. All the others are crossovers, SUVs, trucks, and that could also be an interesting timeline if you look from the Model T to a lot of the very long sedans, and now a completely different style. And the younger generation, I don't know if the preference, correct, are more futuristic. So you could look from all these lenses to see evolution in the industry.
Awesome, thank you. Anything else, folks? You guys are good? Yeah. All right, Karin, so thanks so much for your time today. It was so much for us, we learned a lot with your presentation.
I appreciate you guys having me this afternoon and all the questions. Thank you very much.
Okay, thank you. Take care.
Thank you.
Na chuva, sol e sereno, sozinho aqui desprezado. Hoje ninguém mais se lembra que você abria a picada, abrindo novas estradas, formando vila e povoado. Meu velho carro de boi, trabalhaste tantos anos, o progresso comandando no transporte do sertão. Hoje é traste velho, a orelha do patrão. Meu velho carro de boi, a sua cantiga amarga, no peso bruto da carga, o seu cocão rígido. Meu velho carro de boi, quantas coisas se retrata, a estrada e a verde mata, e o tempo do meu amor. Meu velho carro de boi, é o fim da estrada comprida, puxando a carga da vida, a mais pesada bagagem, e abraçando o cabeçalho